In the previous video, we have seen how to design the fully controlled converter with the resistive load. And after this resistive load, we have set the firing angle to the firing angle alpha to the 30 degree. Now I can change this firing angle alpha here. So I can make this alpha now, alpha is equal to 60 degree, and I can simulate the same circuit once again. So just run this circuit once again with the alpha is equal to 60 degree, and so let's observe the results. Hmm. So for any firing angle you can find the or you can see observe the waveform. So for 30 degree and 60 degree I have observed this waveform. So you can see each SCR is firing after the 60 degree, and this corresponding AC to DC conversion you can see here. Okay, so okay, so now it is visible over here. Now let us see how we can simulate this, sir, how we can add the measurement, how to measure the average value, RMS value, then how to measure the power, active power, AC power and DC power, and how to calculate the rectification efficiency, that we will see in this session. So let's close this, and we will add some we will add some block here again. So again I will take this all four blocks which were there. I will copy this all four blocks again at the downside for the measurement purpose. So this is my Vs, Vs, V0, I0. So these are the entire blocks. Now we'll do the signal processing on all this. So let me add the average and RMS value with the source one, and then we will see for load one. So for source one, I want the mean value. So mean means average value. So click the block of mean. So it will give you the mean value. But if you want to take the mean of the source voltage is bidirectional because it is AC. So if you want this a mean value of this, first we have to take the mod of that. That is absolute value. So click on absolute value first, then add this absolute value here, and you connect here. So you will get the uh, RMS, average value, that is a mean value. Here frequency we have to set by default it must be 50 hertz. 50 hertz. So then here you will get the mean value or average value. How to take the RMS value? So right click, type the RMS. Okay, so you can check the RMS from this electrical specialized block. So you take this RMS value for the measurement. Okay, you place this RMS here. I want source voltage RMS value. Double click to this. Fundamental frequency is RMS value. Initial RMS value I will keep it 0. Okay, so now we want to display these two results. So add the display. Okay, so again one more display, or you can change. Okay, so I will add one more display now. Later on, I will show you how to combine in one display. Okay, so if I run this, so see, source voltage is 100 volt, peak value, so its RMS value must be 100, and average value must be, RMS value is 100, and some voltage drop will be across the SCR, so it is showing the 99.96, and the average value, so it appears the average value as 89.73. Let's verify through the calculation. So what is the peak value? Peak value is 100 into SQRT square root of 2. This is the peak value, and RMS average value is 0.637 times of it. So it comes to 90.08. Here it is showing 89.73 because some voltage is drop across the SCR. SCR is not ideal in this case. So likewise, we have created for V0. Now, similar things we have to do with the other block, so need not to worry about this all other blocks. Just disconnect this. uh, you can copy this. Okay, so you can create the subsystem from this. Create the subsystem. So here is the source voltage I am giving as an input. Here I am getting the mean value. Here I am getting the RMS value. Now the same block I want in the load. So copy this block and connect here. So I will connect this block here. Double click to this. Instead of source voltage, now it is a load voltage. But load voltage is a DC. So as the load voltage is a DC, you need not to take this value as the mod. Mod is not necessary over here. So because this is a unidirectional value, so you remove this mod block from here. So it will give the mean and RMS value. So here you will get the mean and RMS value of the load voltages. Now, similarly, we want to add this block against the load current. Okay, you add this block against the load current and change this name as, or double click, and here you can change this name as, instead of load voltage, I will make it load current. Okay, so this is my load current value. Now again go up. Similarly, I want the source voltage also, but source voltage is again what your source current is again your which quantity, AC quantity. Source current is AC in the nature, so average value will be zero for over a full cycle. So that we have to add the absolute block in the average value. So we'll connect this absolute block in the average value. So it will measure the source current. So I got these four measurements. Let me arrange this all together so that, okay, so it will look good. Now I want to measure the everything in single display. So if you want into the single display, take mux. Sorry, uh, take mux all to combine the all signals. So how many inputs are here? 8 inputs are here. So I will make in mux as a 8, mux of 8 inputs. Okay, so control and click to this. Control, sorry, control, click, con, press this, control, click this, place this control, click this, or you can connect it individually also. Okay, now here uh, I will add the display. Okay, display block as a single. These all are the measurements. So let me combine all these things in the measurement, and now you can run this file once again. So if you increase this, all displays are available here. So first one is average value of the source, RMS value of source, average value of load voltage, RMS value of load voltage, average value of load current, RMS value of load current, RMS value, average value of load current, source current, RMS value of source current. So you observe the RMS value of the currents are same in the load and source side. Okay, So this is the measurement of voltage and Vs and Is. Now, uh, how to how to calculate the power from all this. Okay, so to calculate the power from all this, we need to connect the display blocks once again. So DC power. So let me take the text from here. What is the formula of PDC power? PDC power is nothing but V0 into I0. V0 I0 is your DC power. So let me change its font size. I will make it visible. Okay. So this is the PDC V0 into I0. If I want to calculate the PAC, so how I can calculate the PAC? PAC is from the RMS value V0R into I0R. Okay, R indicates the RMS value over here. So I want to calculate this AC and DC power from this measurement. So I have to add the uh, this I have to add these all uh, V0 multiplication of V0 I0 multiplication of V0 R I0 R, that is the average and RMS values. So I will click here. I will take a block of go to. hmm, First, I will connect this block go to block here. This value is my sorry, I want for the load side. So let me come here and connect this block here. So already V0 name was given to another block. So I will give this name as V01 block. Hmm. Then let me increase this size over here. So this is my V01. Then I need V0R1. Okay, I will make it global first. Wait. Wait, it is giving some error. Okay, so let me change the plan over here. I want to display the AC and DC power. So in the same measurement block, I will try to accompany this AC and DC measurement. So let me increase the areas. Here I need a product block. So I will take the product block. So to this product, first V0, this is my mean value, that is a V0, and this is I0 is added here, mean value of or average value of the other. So and it will give me the DC power. So then I need one more block of this. Here I will give the V0R. So V0R means RMS value and I0R means RMS value of the output current. So here you will get AC power, here you will get a DC power. Let me take a mux. So let me take a mux. I will connect this mux block here. Then again I will take a display. I will connect this block over here. So first we'll measure the DC power and another one will measure the AC power. So let me run it again. So you can observe the AC power and DC power, AC power and DC power. Suppose you want to calculate the rectification efficiency. How will calculate the rectification efficiency? The rectification efficiency N is equal to PDC is the output divided by PAC. So you will get this by this formula. You will get the rectification efficiency. So here I will take a block of divide. In the first block, I will connect the DC power, and second block I will connect the AC power. rectification multiplied, it should be multiplied with the gain of 100. So it will be converted into percentage. So it's 100 gain, I'm keeping this 100, so it will be converted into the percentage. If I want to add the in the same display, what I will to do, I will change this mux dimension, the mux port input ports to the 3, and I will add this third port as rectification efficiency over here, and again run this file. So see, it is, I'm getting this 56.11% is my rectification efficiency. So this is all about the all about with the R load. If I want it with the RL load, so double click this, change this load type to the RL. I need this is a 50 millihenry. So 50. Okay, so let me check what I have given. Not only L, it is RL. Okay, 5 ohm and 50 millihenry. Let me check what I have given in the problem statement. So it is given in problem statement 50 millihenry. Good. So with the 50 millihenry, I am simulating this again. So let me check with alpha is equal to 60 degree. I have kept alpha is equal to 60 degree initially. Same alpha degree equal to 60 degree is there. If I double click to this, you can observe, you click on this. Okay, scale x and y axis limit. So you can see the voltage is on going on negative side. Current is become somewhat continuous. So current is not reaching to the zero. Current is continuous in nature. If you increase the value of the inductor further, this will be again smoother. Okay, so if you want to check the effect of inductor, you change this inductor value. I will change this inductor value to 500 millihenry. So I will increase to the 500 millihenry. Let's see the effect of the large inductance. So due to the large inductance, you will observe that this current is becoming constant after some time. If you increase the simulation timing, it is clearly visible. So let me make the simulation timing to 0.5 and once again run it. So you will observe that after a certain time your current is becoming constant and your source current is almost a square wave. So because of the inductor rate, it opposes to the rate of change of current. So initially the current will not rise to the final value directly. It will take a time to rise to the final value, but after certain times it becomes a steady state. If you want to see the waveform in the steady state, you can click here. Sorry, you can click here, take this tool and zoom to this much only part. So you can observe the source current, source load voltage, load current. So load current is having very small ripple and this is almost constant current. So I have changed this values to the 50 500 millihenry. So now you can make it 50 once again. I will make the simulation timing to the 0.1. Here you have observed the source voltage, source current, RMS value and average value is not changing, but load voltages values are changing drastically. You can check with your theoretical calculations. So here the AC and DC power is also changed. Rectification is efficiency is dropped to the 43.66, 43.36%. Okay, so this is with alpha is equal to 60 degree, but I don't want this voltage which is going on the negative side. I want to clamp this voltage at the zero, but making the current continuous. So I need to connect the freewheeling diode. So I will take one diode from the uh, specialized power electronic family. The diode must be connected across the load in reverse bias position. So double click on diode. I will unclick this show measurement port. So I will connect the cathode terminal on the upper side and sorry, cathode terminal here and anode terminal here. So this is connected across the load. This diode is freewheeling diode is connected across the load. Now let's see the effect of freewheeling diode. So you can observe here the now voltage is not going to the negative side. The current is a continuous in nature, and if I see the values of the rectification efficiency and all average values of the voltage, average values of the voltage is improved here, it is 66, and rectification efficiency is now 73.98%. Okay, so see, with RL load and freewheeling diode, your rectification efficiency is increasing. So this is all about the all three problem statement. I have simulated for alpha is equal to 60 degree. You can try it for alpha is equal to 30 degree. You can change the value of the inductor. So let me change with the very high value of the inductor. Now I will keep the inductor value as 1000 millihenry, or you can say 1 henry. Okay, 1000 millihenry, that is 1 henry. Then okay, so let me change the simulation timing is up to 1 second, and let's see the waveforms. Okay, so you can observe the current is becoming continuous in nature. Here, the current is becoming almost ripple free. That is, it's DC. But if you see this low source current, source is a square wave. So that lots of harmonics are generated on the source side. So if you want to check this harmonics, you can check this harmonics with the scope data. So you can click this. Okay, so come to, I want to save this data in the scope view. Go to the setting, then you click on logging data, log data to the workspace. You record this structure with time, apply, okay. Then in here I want to change one thing from this, otherwise it will not appear in the output window. So let me check where is that. Okay, go in this model setting. Let me data import a process. So I have to unclick this, otherwise FFT window is not available. Single simulation output. This is untick. Okay. Now I can run this simulation once again. Run this simulation once again. Okay, I want to see the total harmonic distortion in output. Open the Power GUI block. Go in the apps. Go in the FFT analyzer. If you come into the FFT analyzer, so this FFT analyzer is used to analyze the harmonics in the circuits. Okay, total harmonic distortion, what is the individual order of the harmonics. So let me bring it downside. So my frequency here is the 50 hertz. I want the source current harmonics and under steady state conditions. So let it is starting time, I want it from 0.7 to 0.9. In this duration I want the harmonic distortion, and if I click on the compute DFT, okay, if I click the compute FFT, it will calculate. You click on FFT window. Oh, sorry. Start time, signal. I want to see from the source current. 0.7 seconds, say how many cycles I want. I want the 3 cycles data. Okay, so that is the 3 cycles data. Instead of signal, I will display only FFT window. So if I calculate the FFT window, FFT of this, so you can observe the THD, total harmonic distortion, is 31%. Fundamental current is 14.17 ampere, but it is THD, total harmonic distortion, is 31%. So source current is get polluted due to the presence of the your fully load converter. So if you observe the source voltage, My source voltage is the sinusoidal one. So THD is very, very small THD. It is 0.52% only THD is there. Okay, and average value is 141. So there is no harmonics in the source voltage, but source current have a harmonics due to the non-linearity of the load due to the switching load. So if you want to see this is in terms of list, okay, if you want to see in terms of list, again you compute this. So you can observe what is the 50 hertz harmonics. 50 hertz is 100% present. It is a relative. If you want the absolute value, okay, so least value, then you can base value as 1. So you can find the 50 hertz current is 14.7, second harmonics is 0.14, third harmonics is 0.016. See, fifth harmonics is the dominant in this case. The fifth harmonics is 2.82 ampere. Seventh harmonics is also dominant. Then eighth harmonics is not dominant there. So this will give you the data about the computation of FFT. So hope you understand how to see the harmonics also in this from this video. With this, we are at the end of this simulation of single phase fully controlled converter with different load. Hope you like this video. If you like this, please share with your friends and subscribe my channel. Thank you.